lecture, we have chosen the orthonormal basis in the two-dimensional Hilbert space. This choice seems to be arbitrary, and in practice it is needed for the measurement of the quantum beat, and it is defined by the particular parameters of the quantum hardware. Now, why would we want to measure the qubit? As you remember, quantum systems, which we employ for computing, are isolated systems. So they reside in some kind of big black box, as you remember from the previous week. And if we don't know the state of the system and we want to know it, then we have to introduce some external part to this system, some measurement device or some observer. And as you remember, this observation does not alter the state of the system. Instead, it records information about the system into the observer and alters the wave function of the observer, like this. Here we denote the quantum state of the observer, and here we have this quantum beat. It is a quantum system, and the observer chooses to distinguish two different states like this. And after observation, we have two different copies of observer, each of them observing different state of the system. So this is how measurement looks like from the multiverse point of view. Now, what we can tell about this measurement process. First, we understand that this observer can choose the states he is going to distinguish. So it is the choice of the basis here, or the choice of observable operator, as physicists call it. And after the measurement, observer subjectively obtains one of these states. So one of these basis vectors, and this is a very important point. When you choose a basis for this measurement, for observation, after observation you will always get one of the vectors of this basis as your measurement outcome. And since for one qubit there are only two possible such measurement outcomes, like two vectors, because the space is two-dimensional, that means that after measurement, after observation, you will receive one bit of information. And for you, after measurement, subjectively, the system will be in this state that you have obtained as a measurement outcome. So subjectively, it will look like you have altered the state of the system, like you destroyed it. It was some combination of vectors before measurement. Like this, we have vector phi here. But after the measurement, the system will be either in the state 0 or in state 1. And the probability to obtain the state 0 as the measurement outcome equals to alpha modulo squared. And the probability to get outcome 1 equals to beta modulo squared. So the closer is vector phi to one of the basis vectors, the bigger is probability to obtain this basis vector as the measurement outcome. Actually, we can compute, for example, this dot product to see that this is alpha 0 plus beta 1, which is alpha, remember we have linearity on the second argument, alpha 0, 0, which is 1, plus beta 0, 1, which is 0. And it is just alpha. And if we take the absolute value, then we see that this is the cosine of this angle theta here. And if we compute this dot product, it will be beta, place modulo, and it will be sine of theta. So probability of obtaining vector 0 is cosine squared of angle theta, and probability of obtaining vector 1 is sine squared theta. Well, I told you that this measurement or observation does not alter the wave function of the system. Instead, it alters the wave function of the observer. But I also told you that the observer here can choose the basis or the states he chooses to distinguish. And after observation, each particular copy of the observer entangles with one of these states and subjectively observes it as the measurement outcome. So the system for this observer here is now in state 1. How is that possible? For example, for vector phi here, we will have the observer which observes 0 and the copy of observer which subjectively observes 1. And these are now the real states of the system. But we remember that the real state of the system was this vector phi. And of course, this observer can choose another basis. And in this case, there will be another vectors here. How is that possible if we don't change the system? From the many-world interpretation, from the multiverse point of view, when we say that the system is in a state phi, that means that among all the snapshots of the universe, among all these copies of the universe which contain this state, the mean value of the state is phi. So it does not mean that in every universe this state is exactly vector phi. We understand it as a mean value over all the copies of the universe. So there are copies of the universe where the state is 0 and where the state is 1. And the shares of these copies in the whole multiverse is defined by these coefficients. So they are proportional to the squares of the modulus of these coefficients. And when we choose some basis here, if we choose, for example, to measure our qubit in the basis 0, 1, then we consider this system only in the universes which contain these vectors here. So let us sum up everything that we learned about the measurement of a qubit. To perform the measurement, first we have to choose the basis or the observable operator. And the measurement outcome is going to be one of the vectors of this basis. Second, the measurement is a probabilistic process, and the probability of obtaining each of the vectors of the basis are defined by the decomposition of the system vector in this basis. Third, subjectively, measurement is destructive, because after measurement, the system for us flips or jumps to the vector of the basis that we obtained as a measurement outcome. And the last one, after the measurement, we obtain only one vector of two possible vectors of the basis, so we obtain 1 bit of classical information from 1 qubit of quantum information. And now some of you may probably ask yourself, is there a way to obtain more? Actually, to obtain these coefficients here via the measurement process. Well, if we run measurement once, we obtain only 1 bit. We don't obtain these two complex values, alpha and beta, which will be extremely nice to know in some cases. And if we perform measurement twice, we obtain always the same result, because, for example, if we obtained 1 as the measurement outcome, the second and all other measurements of this system will give us 1 again, because the probability of obtaining 1 is 1. And the probability of obtaining 0 is 0 for this example. But maybe we can make, for example, 1,000 or million copies of this state, and to measure all these states, to make the estimation not of alpha and beta, but of their modulus, which will give us much more information than just 1 bit. And unfortunately, we cannot do even this, because the non-cloning theorem proved by Wouters, Zurek, and Dyax in 1982 tells us that copying of the unknown quantum states is impossible. So, to conclude, both these systems, this classical system here on the left and this quantum system on the right, have many possible values. Like we distinguish here only vertical and horizontal, but there are much more other directions of polarization. And here we distinguish only left and the right part of the camera, but there are a lot of different actual states of this system. And from the informative point of view, this system here and this system here contain only 1 bit. The process of reducing the number of states on the left is called digitization, and on the right, for the quantum system, we call this process measurement.